We are working through, in this video, number 7 and number 8 in the packet for Taylor Series, worksheet number 2, AP Review. So number 7 says the function f is defined by the power series given by f of x, and for which the series will converge for all real numbers x. And the function g is defined by the power series given here, and for all real numbers for which the series converge. Part A, find the interval convergence of the power series for f. Justify your answer. So to find interval convergence, and we have the rule given here, we can just go through ratio test. So ratio test is a limit as n approaches infinity of a sub n plus 1 over a sub n, absolute value of that expression. Wherever that expression is less than 1 is where the series will converge. So we're going to find the interval convergence for f of x. So we're going to replace every n with n plus 1 to find the a sub n plus first term. So we get n plus 1 times x to n plus 1 divided by n plus 1 plus 1. Divided by a sub n, the same thing as multiplying by the reciprocal of a sub n. So we have multiplied by n plus 1 divided by n times x to the n. Because of the absolute value, we don't have to worry about the alternator. All right, so let's see what reduces here. We see n plus 1 and n plus 1 stays, n plus 2 stays. The x to the n plus 1 will cancel out with x to the n, leaving us with just x up top. So we're left with n plus 1 divided by n plus 2 times n. And as n approaches infinity, if we distribute this through, we're going to have the highest degree being n squared. And if we take the leading coefficients of n squared, it will just produce 1 in front. So all this drops out, leaving us with just x, absolute value of x. So wherever absolute value of x is less than 1 is where the series converge. And if that's the case, then we know the interval convergence will be between -1 and +1. However, we have to always make sure that we test the endpoints. Just because we have the potential interval convergence doesn't mean we know what's happening at the endpoints. So we're going to plug -1 back into the f of x and see what happens. So replace every x we see with -1. We're going to get a positive 1/2, positive 2/3, positive 3/4. So each of these terms, notice that the sequence is not approaching 0. So if that's the case, then by the nth term test for divergence, we know that the series will not converge at x equals -1. Okay, and if we replace, if we want to test the other endpoint, which is at x equals 1, that would just be 1 minus 1/2 plus 1 over 4 factorial minus 1 6 factorial. Oh, sorry, the f of x minus. So -1/2 plus 2/3 minus 3/4. And we see that even though the signs are alternating, the alternating series test is not going to work because we still need the rule of sequence to go to 0, and it doesn't go to 0, or the limit as n approaches infinity for each of these expressions do not go to 0. So we know the series will not converge but diverge at x equals 1. So we don't include the endpoints in our interval of convergence, just between -1 and 1. Okay, part B. The graph y is equal to f of x minus g of x passes through the point 0, -1. Okay. Find y prime and y double prime. Determine whether our function has relative min, relative max, or neither. Give a reason for your answer. So we want to find y prime of x first, and then we can plug in 0 to find y prime of 0. So we're given what y of x is. So if we want to find y prime will just be f prime minus g prime. So f prime minus g prime, we can just find the derivatives of each of these terms and use that to help us find y prime of x, and then y prime of 0. So we're going to take the derivative of each term in f of x. So -1/2 plus 4/3 x minus 9/4 x squared plus ... Which means that f prime of 0, which we're going to find eventually, will just be -1/2, because if I plug in 0 in for x, every term except the -1/2 will go away, because everything will cancel out with x being 0. So f prime of 0 is negative 1/2. Okay. G prime of x, we go through power rule for each of the terms, and just like before, every term except for the first one has an x attached to it. So if we find g prime of 0, sorry, it'll be negative 1/2 as well, not double prime, just prime. Okay, negative 1/2. So then y prime of 0 is just f prime minus g prime. So f prime 0 minus g prime 0, negative 1/2 plus 1/2 is 0. So we know that y prime, the slope at of the y function at 0 is going to be 0, slope of the tangent line. Okay, moving on to the second derivative, because we also want to find y double prime of 0, which is y f double prime 0 minus g double prime 0. So what we can do is we can find the second derivative, and we're left with 4/3 minus 18x over 4 plus dot dot dot. G double prime of 0 is 2 over 4 factorial minus 6x over 6 factorial plus dot dot dot. Replace each of the x's with zeros to find f double prime and g double prime. We get 4/3 and 1/12. So then y double prime of 0 is just 4/3 minus 1/12, which is 15 over 12, which is positive, greater than 0. And then what part B is asking for is determine whether our y function is a relative min, relative max, or neither. So by the second derivative test, we know that if the slope, if y prime of 0 is equal to 0 and y double prime is greater than 0, so that means that if the slope of the tangent line is 0, okay, and that point is part of a concave up graph, then we know that the graph must be, that point must be a relative minimum at x equals 0. Okay, let's look at number 8. All right, so let f be a function with derivatives of all orders for which f of 2 equals 7. When n is odd, the nth derivative of x at x equals 2 is 0. When n is even and n is greater than or equal to 2, the nth derivative of f at x equals 2 is given by the nth derivative evaluated at 2 is n minus 1 factorial over 3 to the n. So part A says write the 6th degree Taylor polynomial for f about x equals 2. So to build our Taylor polynomial using Taylor's rule formula, we can do the summation from 0 to k of the nth derivative evaluated at c over n factorial times x minus c to the nth. So if we build this, we know that every other term will, all the even derivatives will cancel out, will just go to 0. So I'm just going to write the first term and then the term associated with the second derivative, and the fourth derivative and the sixth derivative. Okay, so I'm just following this formula, this rule here. Now, based off of all the values, this rule that we can then use to evaluate the second derivative at 2. So we can just plug 2 in for the n values. So 2 minus 1 over 3 squared will just be 1 over 3 squared over 2 factorial. And then the fourth derivative value at 2, just plug 4 in for n, so 4 minus 1 over 3 to the fourths over 4 factorial. And then plug in 6, 6 minus 1 is 5, 5 factorial over 3 to the 5th, 3 to the 6th, sorry, over 6 factorial. And if we clean this up a little bit more, we get 7, and then this 2 we can bring up and share the same denominator space as a 3 squared, so we get 1 over 2 times 3 squared. The 4 factorial can come up and share the same denominator space there, and the 6 factorial comes up, share the same denominator space. Now, for part B, it says, in the Taylor series for f about x equals 2, what is the coefficient of x minus 2 to the 2n for n is greater than or equal to 1? So we're trying to figure out a rule that represents the coefficient in front of the x variable. So we need to create a rule based off of the pattern that we see. We can then use this as n equals 1. This is this is for n is greater than or equal to 1. So this represents n equals 1. So when we plug 1 into this expression, we need to get this in return. We plug 2, we get this in return. If we plug 3 in for n, we get this in return. Now they're telling us that the exponent above the x will just be 2n. So if this is 2n, then 1 times 2 will be 2. That makes sense. If this is 2n, then 2 times 2 will be 4. If this is 2n, then 2 times 3 will be 6. So we just need to kind of work with these coefficients to make sure that our patterns will match. So in order for us to be able to plug n equals 2 and get this in return, we know that this is going to be 2n, but this is always going to be 1 less, and it's always going to be an odd number. So if this is 2n, then this must be 2n minus 1, right? If this is 2n will produce 4, then 2n minus 1 will produce 1 less than that, an odd number. So to create odd numbers, we always start off with an even expression, 2n in this case, and then we subtract 1 from it, or add 1 to it. In this case, we subtract 1. Okay. And notice the 3 is always the same here as 3 squared, and 3 to the 4th, and 3 to the 6th. So we know that it just be 3 to the 2n because we want this exponent to match that exponent. And then here, the same thing will be 2n factorial as well, 2n factorial. So that's what we have the rule to be here. Right? Now we can simplify this a bit more because 2n minus 1 factorial will be 2n minus 1 factorial times 2n minus 2 factorial, so on and so forth. And then 2n factorial is 2n times 2n minus 1 factorial times 2n minus 2 factorial. So anything less than 2n, lower than 2n factorial will cancel out with this expression. So then that leaves us with just 2n in the denominator, and with 1 in the numerator, and 1 over 3 to 2n times 2n. All right. Part C says find the interval of convergence of the Taylor series for about x equals 2. For f about x equals 2, show the work. So we've created a pattern that we can use for our general term. So here's our general term for f of x. And we can then use ratio test to find the interval of convergence. So it's a sub n plus 1 divided by a sub n. So a sub n plus 1, replace every n we see with n plus 1. So that's what we have here. Divided by a sub n, same thing as multiplying by the reciprocal. And if we distribute this exponent through, 2n plus 2 will cancel out with a 2n here, leaving us with just x minus 2 quantity squared. 3 to the 2n will cancel out with 3 to the 2n here, but this is 3 to the 2n plus 2, so we're still left with 3 squared. And then 2n over 2n plus 2 will remain. So limit as n approaches infinity for this expression for as n approaches infinity. Notice that the degree is the same, so we take the leading coefficient, which just left us with 2 over 2, which is 1. And then we're left with this expression. So we know the series will converge as long as this expression is less than 1. So if we try to clean this up, it's x minus 2 quantity squared. Multiply the 9 over through, so x minus 2 squared is less than 9. If we take the square root, it's x minus 2 is less than 3. So absolute value of x minus 2 is less than 3, which means that 2 is the center and 3 is the radius because it's in the form of absolute value of x minus c is less than r. We can write this as x minus 2 is between negative 3 and positive 3. Then if we add 2 to every term on in each position, we get negative 3 plus 2, which is negative 1. Negative 2 plus 2 is 0, leaving us with just x. 3 plus 2 is 5. So we have our potential interval of convergence, negative 1 between negative 1 and 5. But we also have to remember to test our endpoints. So if we plug 5 into our rule of sequence, 5 minus 2 is 3. 3 to the 2n will cancel out with this 3 to the 2n. We're left with 1/2 times 1 over n, which is going to be a harmonic series, which we know will diverge. When x is negative 1, negative 1 minus 2 is negative 3 to the 2n. Negative 3 to the 2n will always be positive. So this will cancel out nicely with 1 over 3 to the 2n, leaving us with just same thing as before, 1 over 2n, which also diverges, not converge. Sorry, this should be diverge. Okay, diverge by harmonic series. So we know that our endpoints will not converge. So our interval is open interval from negative 1 to 5 is our interval of convergence.